Hi everyone. First an announcement, maybe several announcements. First announcement, next time we have a quiz in the last 10 minutes of the lecture. And the quiz is on material from, well, all the material up to today, not including today. So exponential functions, logarithmic functions, limits. Basically just this. Another announcement, well, we didn't cover squeeze theorem last time, and actually several other sections also didn't cover even more material. So the deadline to submit the web work was extended all the way up to Thursday morning. So if you still have doubts about some problems, you can go and make corrections. The third announcement, many people asked about problem number 12, and I posted a solution on the website. You can find it. And well, if you still have questions, come to my office hours, so I will be glad to explain. Okay, so any questions about please call for anything. Sorry? It would be a business question, yes. Yes.
So is the quiz based on the first assignment that we have done?
Say it again.
So this quiz is based on the assignment that we have done?
So the quiz is not based on assignments, it's based on assignments plus suggested problems. Other questions? Yeah.
Where are the suggested problems?
If you go on the main website to the weekly goals, for
Okay.
each week you'll find suggested problems. Other questions? Yeah. Over it? Yes, it would. So the question was, would it be about exponential logarithmic functions? Yes, it would be.
So squeeze theorem isn't on the quiz?
Squeeze theorem is not included. Okay, so since we said squeeze theorem, let's actually discuss what it is. So, well, you might have already read or listened to somebody explain what is squeeze theorem, so I'll just explain when and how we actually use it and, well, what it is. So a typical situation. So a typical situation in which you would want to apply arguments like in squeeze theorem is when you are trying to compute such a link. So let me explain what happens here. I take x and multiply it by sine of a very complicated expression. Yes, e to the power x. So I included here a very complicated expression. Really complicated. When x is small, it's hard to understand what is e to the power 1 over x. 1 over x is large, but it will be positive or negative. E to this power is small. I mean, you'll have to argue really hard to know what happens to this expression. However, you don't have to. The reason is that after we compute this number for any value of x, we apply sine. And sine has a very special property. So I hope that most of you have seen a sine, but even if you haven't, I'll just draw its graph and you'll see its main property. Well, main for this purpose. So its graph is a graph of oscillations like this, continuous, indefinite. And these oscillations happen between the bounds -1 and 1. So once you reach 1, well, you go down, then you reach -1, you go up. And you continue in this fashion. So sine of any number is bounded between -1 and 1. So what happens in this limit computation? We take x, which is, well, when x approaches 0, it means x is a small number. and then you multiply it by a sign of something, which means you multiply it by a number between -1 and 1. Well, now what happens? You take a small number and multiply it by some number from -1 to 1. Well, it's still a small number. Nothing really happens. I mean, it might be a different small number, but it's still small. Conclusion, this whole expression is a small number, and the whole limit becomes 0.
Always because it's
Question? Okay, so that's the essence of squeeze theorem. So we basically applied squeeze theorem in a situation, well, we didn't say it was squeeze theorem, but actually we already applied it. And, well, let me now formulate what is squeeze theorem. And you see that it's just kind of the same arguments, but slightly more abstract. So if you have a function, but you don't really know much about this function. Instead, you know that it's bounded between usually some simpler functions. It's between g1 of x and g2 of x for any s. And you know that when x is close to some point, both g1 of x and g2 of x are close to some number L. So what's written here, when x is close to some point A, both g1 of x and g2 of x are close to number L. Conclusion, because f of x must be between these two numbers for every x, and these numbers are close to L at this point, f of x is also close to L. So conclusion, then limit as x tends to A, f of x is equal to this number L. So once again, the argument is very simple. Since when x is close to A, both g1 and g2 are close to L, and f is, well, it must be between this number and that number, but they are both close to number L. It means that it itself is close to number L. So this limit is L. We can also interpret it graphically. If you have on one graph the graphs of g1, g2, and f, the picture looks like this. You have graph of, say, g1, g2, you graph g1, and at some point A, both of them are close to some value L. Now you don't know really much about the function f. The only thing you know is in between. So it means its graph is somewhere between these two graphs. Well, it could wiggle, it could oscillate, it could do crazy things, but as you approach the point A, because it is between these two graphs, it must be also close to this number L. It has just no choice. And that's exactly what happens in this situation. In this situation, we really apply this squeeze theory. We argued, so back to example. The way we argued was as follows. Sine of, well, this complicated expression is always between -1 and +1. Hence, f times sine of this complicated expression. I really don't even have to know what this complicated expression is. But I can argue that it's between x and -x. Also, we know that limit as x tends to 0 of both this function x and -x is equal to 0. So our number is bounded between two numbers, both of which are small when x is small. Conclusion, it is also small, or in other words, the limit of this expression is 0. Hence, by squeeze theorem, limit x sine of whatever the expression was, plus x 100 plus x is equal to 0. So that's the way we'll write it on quiz on the exam. So instead of just writing and explaining long strings of words like when x is close to something, we'll just say, well, in general we already argued once, and we call such kind of argument squeeze theory. And now we can just apply it. We bound our function between two functions whose graphs touch each other at some point, and hence our limit in question must also be equal to this value right here. Okay, so any questions about this theory? Most often you will encounter it exactly in this situation when you multiply some simple function by some oscillating function, but something which oscillates, well, kind of like sine of something, cosine of something. Okay, let's then switch to the main part of the lecture today, and it's about continuity. Before I talk about continuity, I want to talk a little bit about discontinuity. What does it mean when we have a discontinuous process? A break, yes, something like this. So let me introduce a process, show a process which, well, might have a discontinuity. So here's a ruler, and I will try to apply some force to it. First I'll apply small force, and the ruler bends a little bit. I apply more and more force, and bends more and more. Well, at some point I'll apply more and more and more and more force, and at some point something drastic will happen. Okay, so now let's see. What is the mathematical abstraction? So you see that something really drastic happened. It was very nice, very controlled, up to some point. At some point it really got out of control. And I really couldn't trace what happened to the ruler after this point. And in the graph it would look like this. So if this is the graph of, say, position of the middle of the ruler, well, actually here it is now, the middle of the ruler. From, well, depending on the force. So here is the force, and here is position of some point on the ruler. So I start with applying no force, and the position is at 0. Then I apply more force, ruler starts bending. Well, I apply more and more force, it now resists bending. It now bends less and less and less. And at some point, well, I apply even more force, and suddenly something drastic happens. The ruler flies off, well, goes in the room, well, I don't know what happens. So the main, well, for us, the critical point will be this one. What happens at this moment? Well, the phenomenon is characterized with the following thing. Here the change is very controlled, very nice. Here it's sudden and big. So we would want to say that the function of this shape is continuous here, continuous being, well, meaning it is actually, well, controlled, occurring slowly, kind of changing a little bit. And here it is discontinuous. Something very drastic happens, it jumps. So mathematically we'll say use the following definition. A function f of x is continuous if a small change in argument leads to a small change in value of the function. So here, my process used to be nice and continuous all the way until the following, all the way while the following holds. If I apply just a little bit more force, the position changes just a little. So if I apply a small force, small additional force, the change in position will be small. At the point of discontinuity, that's no longer true. So if at this point I apply just slightly bigger force, the change in position will be drastic. Well, this definition is a little bit imprecise. I mean, we should talk about kind of what does it mean, small change, and I mean we have to explain stuff here, but we have a very nice way to rephrase this definition. So better definition. So I would say this kind of informal definition is what we would like continuity to be. And the formal definition, well, it will be something that you can actually verify given a function. So the formal definition would be like this. F is continuous at point x equal to a if limit as x goes to a f of x is equal to value of f at the point a. Let's see that this definition is really not that different from the first one. It's actually the same definition, but about 1 point. So the second definition is about whether a function is continuous at some point. So we choose the point A, and what does it mean for a function to be continuous according to this definition? It means that when x is close to A, f of x is close to f of A. And the closer x gets to A, the closer f of x to f of A. So indeed it is about a small change in x value here. If x is close to A, leads to a small value, small change in the value of the function. If x is close to A, f of x is close to f of A. Which is of course wrong at this point. Here the limit as x tends to A does not exist. Because, well, from one side it's one thing, from another side it's quite different. So here in the book you have a large jump. Okay, this definition can be. Question? So this definition can be used to check for continuity. Given actual function, how do we check for continuity? Well, here's an example. Is f of x, which is x squared plus 1, continuous x equal to 2. Well, it's a very simple question if you just follow the definition. The answer, well, what do we have to check? We want to check that the value at the point 2, which is 2 squared plus 1, which is 5, and the limit as x goes to 2 x squared is close to 2 times 2, which is 4. So x squared plus 1 is close to 5. So the limit is 5. And the two values agree. So f of 2 is equal to limit as x goes to 2 of x. So f is continuous and x equal to 2. Well, and of course, this doesn't really is what we would expect. The graph of this function is just a parabola, and you do know that the parabola is a very nice graph, no breaks on it, nothing drastic happens. So in fact, this function is continuous at any point, not just at x equal to 2. But it's nice to confirm our intuition now. More interesting examples happen when something is not continuous. So let's have some such examples. Let me have such a function. X is the value of x. Let me start with such a function. X over x. And the question is, let's start with an example, is f continuous at x equal to 0? So maybe any cases. Is it continuous? Okay, why?
Just a flat line.
Okay, so the argument is its graph looks exactly like a flat line. Whenever, well, for any x, the value of x over x is equal to 1. Okay, that's right, but that's almost right. If I had written instead f of x is equal to 1, that would be correct, and this function would have been continuous. However, for this expression unfortunately is not defined at x equal to 0. You just cannot plug in x equal to 0 and get an answer. 0 divided by 0 is not defined. So I'll have to say that my function, the one defined here, is not defined at the point 0. I'll put a small circle to say that, well, there is no value here.
There's also no negative, is it?
Sorry?
There's also no negative number. Oh no.
It is actually equal to 1. So x over x is always equal to 1, except when x is equal to 0. And according to this definition, well, let's check. So answer f at the point 0, the value at the point 0 unfortunately is just not defined. So even though the graph looks almost perfect, it's almost a straight line, we'll have to say that this function is not continuous. It just doesn't satisfy this definition. So f is not continuous. The intuition behind this is, well, a continuous function, a graph of continuous function is a graph that you can draw on your paper without lifting a pen off the paper. Or in my case, chalk off the board. And this graph is not exactly like this. It's almost like this, but here you'll have to make a break. You don't want to go through the point x equal to 0.
You can still find the limit of that, right?
Yes. Yes. So indeed, the limit as x tends to 0 here does exist. So limit of f of x as x tends to 0 does exist. It is equal to 1. So it seems that we can actually repair this function, define it to be at 0, to be equal to 1, and that will make it continuous. So let's check that it actually does work. I'll continue here. So now another example. F of x is now defined by this formula whenever x is non-zero, and at the point 0, let me define it by 1. Now this function is continuous at the point 0. Because, well, f at the point 0, by definition, is equal to 1. The limit of f of x as x goes to 0 is the limit of x over x as x goes to 0, which is 1. And they do agree. So f of 0 is the same as the limit as x tends to 0 of f of x. So this definition is satisfied in this case. And of course, the graph reflects it. The graph of that function is the graph of this function together with one additional point. At the point 0, the value is equal to 1. So we insert this missing point. And now it becomes continuous everywhere. In fact, this function is identically equal to 1. For any value of x, 0 or non-zero, the value of the function is equal to 1. So there is no difference between this function and the function which is just 1. Even though it's written in a more fancy way. But if we are not careful enough, we would spoil the function. Instead of making it continuous, we would make it even more discontinuous. So another example, if instead you define this function to be 5 at the point 0, then it will become even less continuous than it used to be. Now it's kind of beyond repair. Because its graph looks like this. It's 1 all the way up to 0, then it continues with 1, but at point 1 it suddenly is 5. So now you do have, well, quite drastic jump from 1 to 5, back to 1, and all this happens in kind of 0 time. So it is discontinuous x equal to 0. So the problem here is that value f at the point 0, which is 5, is not the same as the limit f of x as x goes to 0. This is 1 and this is 5. So all these examples kind of give you a checklist, how to check that the function is continuous at the point. So to check that the function is continuous, at some point x equals to 8, we'll verify several things. One, you don't want to be in these situations. F should be defined at the point. Limit, f at the point A exists. You also want to have a limit. When x is near the point A, you want to know that your function, well, becomes close to something. Limit as x goes to A f of x exists. We'll see an example in a second where this is violated. And third part is the two values agree. F at the point A is equal to the limit. So every time you want to check that the function is continuous, you check three things. The function is defined at the point, it has a limit, when x is close to the point A, f of x is close to some number. And finally, the two numbers agree. There is no strange we haven't seen for now a function which is discontinuous and kind of irreparable, which you cannot change to make continuous. Let's see such an example. Example, f at the point x. So here's a function. For every non-zero value of x, it's defined to be absolute value of x over x, and it's defined to be 1 at the point 0. So it's defined for every x. Is it continuous at the point 0? Why not? Which one of these is violated? What's wrong with it? Well, let's go by one. Is f defined at the point 0? Yes, here it is. So, is f continuous at 0? That's the question. And answer, well, first we check f at 0 is defined. It is equal to 1. Second thing, does the limit exist? Limit as x tends to 0 of f of x, which is the same as limit of absolute value of x over x. What about this one? Does it exist? Right, it does not exist. The reason is the limit from the right, when x is positive, is equal to 1. When x is negative, however, absolute value of x is, well, the positive number, x itself is negative, the quotient is negative 1. So this does not exist. The limit from the left does not agree with the limit from the right. So this function is not continuous. Hence, f is not continuous. X is 0. And the graph of this function looks like this. It's minus 1 all the way up to 0. At 0 it's defined to be not minus 1 but rather 1. And it continues to be 1. So it's a kind of switch function. It's minus 1 all the way here, and then suddenly it switches to be 1. And you see that there is no way to redefine it to be something at the point 1. That's not the problem. The definition at the point, sorry, at the point 0. The definition at the point 0, well, it's okay. It is defined what it is. As it is defined. The problem is with the limit. When x changes slightly to one side, the value of x is really different from the value of f when x changes slightly to the other side. So that's the problem. Sometimes you might be given questions how to make a function continuous. Let's see once again an example. So the question is, function is defined by such a formula. When x is not equal to 1, it's x squared minus 1 divided by x minus 1. And it is defined to be a when x is equal to 1. So I don't tell you what is the definition of f when x is equal to 1, but I tell you that it is defined in such a way that the function is continuous. So if f is continuous, x equal to 1, what is a? So what should they do? So A is equal to 2. How do we find it? Let's see. So we want this function to be continuous at the point x equal to 1. We'll just follow these steps. We'll check each one of those. So first observation, what is f at the point 1? Well, according to definition, it is equal to a. Second step, what is the limit as x goes to 1 of f of x? Well, when x is not equal to 1, which is close to it, my function is defined by this formula, x squared minus 1 over x minus 1. And I can easily compute this. I can factor the numerator as x minus 1 times x plus 1. Cancel out the x minus 1 and get that the limit x plus 1 as x goes to 1 is equal to 2. Okay, so the first two conditions hold. Function is defined somehow at the point 1. The limit does exist and it is equal to 2. The third condition tells you the two should agree. So third condition tells you A, so f at the point 1 must be equal to the limit. So it means that A is equal to 2. Once again, you can imagine what we just did graphically. If you have a function which is defined by this expression, for every x which is not equal to 1, it is the same as just x plus 1. So, except for the point 1, it is like this, just a straight line. The only problem, at the point 1, it is not defined. Our expression happens to be not defined. And the question is, can you make value of the function at the point 1 to be equal to something so that the whole line will become now continuous? Well, of course, if you just fill this point, you'll get a continuous graph. If you miss it, if you put it too high or too low, you will have a discontinuity. So there is really only one choice to make, and that's the choice that we found. Okay, so any questions about definition of continuity? Let's see now some simple rules which will allow us quickly to determine whether something is continuous or not. First rule is very simple. Many functions that you know are continuous. That's the rule. So functions x to some power, something to the power x, 1 of x. Absolute value of x, sine of x, cosine of x. So all these functions are continuous whenever defined. So all these familiar functions, power functions, exponential function, logarithmic function, absolute value, sine, cosine, they are all continuous Well, whenever defined. So, example. F squared is continuous everywhere. Another example. X to the power minus 1, which is really 1 over x, is continuous for x which is not equal to 0. So at the point 0 it's not defined, so obviously it's not continuous there, but otherwise it is continuous. Another example, ln of x is continuous, so where is logarithm continuous? Where is it defined? For what values of x is it defined? For positive, right. So when x is positive, you can compute its logarithm. When x is negative, you can't. So the function logarithm is continuous. Its graph is, let me remind you how the graph looks like, so that you'll see that it's really, really continuous. It looks like this. This is point 1. Okay, so that's the first rule, very simple. Second rule is you can take these functions and combine them into sums, products, differences, quotients, and still get continuous functions. So rule number 2, if f and g are continuous at some point, then f plus g, f minus g, f times g are continuous at this point. So there is never a problem with taking sums, differences, products. There might be a small problem with taking a quotient. So what's the problem with taking a quotient? Yes, you can't divide by 0. Denominator might vanish. So if g at the point A is not 0, then f over g is also continuous. Let's see some examples. X to the power 100 plus 1 of x plus e to the power x times x squared. So we take such a function and we look here. This function is, well, the parts of this function. X to 100 is continuous everywhere. 1 of x is continuous when x is positive. E to the power x is continuous everywhere, x squared is continuous everywhere. So parts of this function are continuous, well, for x which is positive. Now, the product, according to this rule, is continuous. The sum, well, is continuous. Another sum is still continuous. So this whole thing is continuous for x which is positive. Another example. If you take the square root of x divided by x minus 1, so now I take a quotient. When is it continuous? Well, square root of x, when is it continuous? Right. So according to this rule, it's continuous whenever it is defined. It is defined only for non-negative values. So this is continuous for x which is not negative, and also because I'm dividing by x minus 1, which could become 0, exactly x equal to 1. So I should put a restriction, x is not equal to 1. But otherwise, this function is continuous. And last rule. harder to formulate. But we'll see right after formulation, we'll see some examples, and you'll see that it's really simple. So if g of x is continuous, x equal to a, and f of x is continuous at g of a, then f of g of x is continuous at x equal to a. So this rule takes a little bit more effort to decipher. So we are talking about the function decomposition. You take first g, and then you apply f to the result. And we want to understand, is this function continuous at point A? Well, first look, so what does it mean? It means small change in parameter should lead to a small change in the composition, f of g of x. Well, so first, we make sure that small change in parameter x leads to a small change in parameter in g of x, value of g. So that's this condition, g is continuous at point A. Well, and now you take g of x as an input to the function f. So you want to make sure that f doesn't change much if you change g of x, well, in the neighborhood of the point g of a. So when g of x is close to g of a, you want f of the application to be close to f of g of a. Let's see some example, so that we see that it's actually not that complicated. So example, let's take a composition 1 of x squared minus 1. And the question is, when is it continuous? So this is really a composition. You first take x, then you compute the number x squared minus 1, and once you computed this number, you apply logarithm. So to make sure that this composition is continuous, well, let's check that first step is continuous, and it is. For any value of x, x squared minus 1 is continuous operation. But then you would want to make sure that logarithm is continuous, well, near the point that you put inside of it, near its argument. So you know that logarithm is continuous whenever its argument is bigger than 0. But what is its argument? The argument of logarithm of this function is x squared minus 1. So this is continuous for, well, when the argument of logarithm, which is x squared minus 1, is positive. Maybe x squared is greater than 1. X is either greater than 1 or x is smaller than negative 1. So x will be, for example, negative 2, then negative 2 squared is 4, which is greater than 1. So you see that here we knew that logarithm is continuous for when its argument is greater than 0, and then we did this trick. This outer function logarithm had to be continuous at the value of the inner function, which is x squared minus 1. So in our problem it translates to x squared minus 1 should be, well, inside where logarithm of continuous should be positive. Maybe another example. E to the power 1 over x is continuous. So maybe somebody told me what I should write. When x is not 0, right? When x, so for x different from 0. So here the problem is, so here once again, I compute my function in 2 steps. I take x, I compute 1 over x, and then I compute e to the power of the number that I got in the previous step. So here the problem is at the first step. At the first step, when I compute 1 over x, I might get a discontinuity. I do get a discontinuity at point 0. But otherwise, it's a very nice function. For x which is not equal to 0, it is a nice function. And then I apply a function which is continuous everywhere. So there are no problems with it. So the answer is just like this. Well, and using these rules, 3 simple rules, you can check continuity of basically any function that is given to you by a formula. If you just try any complicated expression, you will be able to determine when is it continuous. So a problem might occur well, when a function is defined kind of by cases. In one case it is something, in some form it's given by one formula, in another one it's given by another formula, then you want to decide whether something happens in between these cases. So let's discuss such a function. So f of x is given by such a formula: x squared plus 1, and x is greater or equal than 2, x minus 1 is small. So this function is obviously continuous, so f is continuous for x which is greater than 2, because it's defined for x which is greater than 2 by such a nice formula, well, obviously it is continuous. Also f is obviously continuous for x which is smaller. The only question is what happens at the point 2, and for this we'll have to compute, well, the value of f of x, f of 2, the limit as x tends to 2 of the function, and whether they agree. So f x equal to 2, well, first step, f at the point 2 is defined to be by this formula 2 squared plus 1, 5. Limit as x tends to 2 of f of x. Well, this limit, we know how to deal with such a thing. Since the function has different definitions from the two sides, it's better if we compute the limit from the right and the limit from the left. So for this, we first compute limit from the left side, which is when x is smaller than 2, I use the second formula, x minus 1, and I get 1. The limit as x tends to 2 from the positive side, so from the right, x. Well, when x is greater than 2, I use the first formula, x squared plus 1. And it is equal to 5. So you see that the limits do not agree. It means that the limit itself does not exist. So limit as x tends to 2, x does not exist. And conclusion, this function is not continuous at the point 2. a rather simple conclusion. No problems with it. I just wanted to say that, well, in this case, we have to compute the limit from the right and the limit from the left. I do want to use this as an example for another point. Sometimes we want to understand whether the function is defined on some interval. For example, well, in this example with the ruler, I did my bending, and I would be interested maybe in what happens in the interval from 0 seconds to 5 seconds. And then I really disregard everything which happens before the 0 second and after the 5th second. So it means instead of kind of treating my original function, I will restrict my function to one interval from 0 to 5. And then you might have some slightly surprising conclusions. So let's suppose that this function from our example will use this function to make some point. So suppose I want to talk about this function for values of x which are only greater or equal than 2. Then I forget about what happened when x was smaller than 2. So if f is restricted to x which is greater or equal than 2, then this function actually doesn't have any problems. Then f becomes continuous. If x is defined by just the formula x squared plus 1 or x which is greater than or equal to 2. So if you look at its graph, the graph of this function, f itself looks like this. It is a parabola like this all the way up to 1, and it is a different line, something like this, when x is smaller. That's the graph of the function. So you see that at the point 2 there is some discontinuity. However, if you just forget about everything that happened before 2, you do get a very nice continuous function. You can draw this graph without lifting a chalk off the board or paper off the pen off the paper. So when you restrict your consideration only to these intervals, you get a function which is continuous. So in this case, we say that f is continuous on the interval x greater or equal to 2. So I want to make a point that when we say that the function is continuous in a certain interval, we mean that once you restrict this function to this interval, you get a continuous function. What we do not mean is that the original function used to be continuous at every single point of this interval. So the original function f at the point 2, at this end point, was not continuous. But when we say that f is continuous on some interval, we actually mean a different thing. We mean that once you forget about everything which is outside this interval, the function is nice and continuous. So let me write this. They think so. We say f is continuous on an interval So let's go back once again to this example. So that our function, which is x squared plus 1, when x is greater than 2, greater or equal than 2, and x minus 1, when x is smaller than 2, and look at it on a different interval. Is f continuous on such an interval, x smaller or equal than 2. So instead of looking at this part, I want to look at this part. No, why not?
Because we included two, which is also.
Say it again.
We included the two.
Right, yes. If I look at this part, x is smaller or equal than 2, then how is my function defined on this thing? Well, its graph looks like this. All the way up to the point 2, it is very nice function, linear function. At the point 2, it is defined not by this formula, but rather by the other one. It suddenly becomes not 1, but rather 2. This function is obviously not continuous. So here the problem is, well, if I restrict my function to this interval, I would be able to compute a limit as x goes to 2, but only kind of from the left. And this limit already does not agree with the value of the function at this point. So no, and the reason for this is limit as x goes to 2, but now I'm only allowed to take values which are smaller than 2. So I'll say limit as x goes to 2 from the left. F of x is equal to 1, which is not the same as the value of the function at the point 2. So in this case, we say that the function at this point is not continuous from the left, but it is continuous from the right. So if you restrict to points which are greater than 2, the function is very nice and continuous. So we say when f of x is continuous from the left, f x equal to a if as you approach a from the left, the values of f become close to the value of f at the point A. And similarly for continuity from the right. Same thing for right continuity, the condition would be limit as x goes to a from the right side, f of x is f. So I just introduced two new words, continuity from right and continuity from left. So sometimes the function might be not continuous at a point, but it is, well, partly continuous. It might be continuous from one side, but not continuous from the other side, like it is here. This function is continuous from the right side, but not continuous from the left side. Any questions so far? So let's solve some simple problem. Example. Sometimes you will ask the question of the following type. Determine the largest intervals square of x when x is positive and minus x minus 1 when x is smaller or equal to 1, k is greater than 0, is continuous. And the way to approach such a question would be as follows. First thing to check, well, obviously it is continuous when x is positive. Obviously it is continuous when x is negative. The only problem that might happen is 0. So first thing to check is whether f is actually continuous at 0. Sometimes it might be. And then the answer is it is continuous for every x. So step 1, check continuity at this funny point at x equal to 0. And we know, well, we see from here that first of all, f at the point 0 is equal to -1. For the limit, we see we'll have to compute two limits, from the left and from the right. The limit from the left, f of x, is limit using this formula, minus x minus 1, so it's -1. And limit from the right, of f of x. Now we use this formula, square root of x. Well, luckily for us, we can compute square root of a positive number, so it is 0. And you see that the two do not agree. It means that the function is not continuous at the point 0. So our interval in which function is continuous cannot include the point 0. So we basically can have such interval from minus infinity to 0 and from 0 to plus infinity. The only question is, would we include the point 0 in one of those? Well, let's write the answer. My interval would start from one of the intervals starts from minus infinity, continues all the way up to 0, and the question really include the point 0. So if I do include it, I would want my function, once you restrict it to the whole interval, to be continuous. Well, let's see. If I include the point 0, I would want my function to be continuous from the left at this point. And you see, yes, you see it is continuous. So here I do include the point 0. Once I restrict my function to this interval, I get a function which is just like this, minus x minus 1. No problems in it. And there is one more interval. It starts at the point 0, continues all the way to plus infinity. But now here I cannot include the point 0 in the interval. I should exclude it. The reason is, well, my function from the right, it's not continuous. The limit from the right being 0 is not the same as its value. So if I do include 0, I'll have a problem. A sudden jump from this value to this limit. Okay, maybe just one question. How many of you have never seen such notation for intervals? Okay, so several. So there's really nothing to be scared about here. It's just, well, basically just notation. So notation, say that x is in such an interval from a to b with open brackets if x is between a and b, like this. We also say that x is in such an interval from a to b, now including the point a, if x is between a and b, including the point a. So it's just about annotation. It denotes such an interval this way, such an interval this way. Also, there are some more combinations, open bracket of A and closed bracket of B. So here we mean that x is between A and B. Now it could be equal to B. And finally, x is in such an interval if x is between A and B, but now it could be either A or B. So it's basically just a notation. Here we mean just x is smaller or equal than 0. N of course greater than minus infinity, but any number is greater than minus infinity. It's just x is smaller or equal than 0. So basically you just have to remember these things. Yes.
So the question is determine the largest interval and if the first interval larger than the second one.
No, so the largest interval observed. So it's about, it might include several answers. So it's not about this interval being larger or smaller than 1. It means that each one of those cannot be enlarged. That's the meaning of the largest interval. Okay, so one last piece of information for today. It's called intermediate value theory. So this thing is actually an almost obvious statement. Let me first state it and then I'll explain what it means. So the statement is like this. If f is continuous on an interval from A to B, meaning once you restrict it to this interval, it is a very nice continuous function. Suppose also that f at the point A is smaller than some number. And also suppose that f at the point B is bigger than this number. So at one of the endpoints, it's the value of the function is smaller than something, and the other one is greater than something. Conclusion, then f at some point C is equal to m for some C in between. I said it's almost obvious, and it is. Let me explain. We have an interval from A to B, and we give some number m. And what we know is, on this interval, my function is nice and continuous. So its graph is something you can draw without lifting a pen off the board, of the paper. At the point A, the value of the function is smaller than m. At the point B, it's greater than m. You don't know what it is. Just one is smaller, the other one is greater. And the question is, will there be a point in between where the value will be exactly equal to m? Yes, because I'll have to go from this point to this one by drawing some line, which is nice and continuous. So at some point I'll have to cross this line. I start from below, and at some point I'll have to go above. It might be not only one point. It might be something like this, and I'll have 3 points. But there will be at least one. If you want to go from below a line to above this line, you either have to jump, which will make your function discontinuous, or cross this line. So that's intermediate value theory. And it looks, well, kind of deceptively simple. It looks now even simpler than it actually is. So let me give you an example that shows that it's actually powerful, not just kind of funny and obvious statement. Example, show that x cubed plus x plus 1 is equal to 0 has a solution between -1 and 0. So the question might seem not really related. I have an equation, complicated equation, x cubed plus x plus 1 is equal to 0. I don't see any obvious solutions to this equation. But I also don't ask you to find a solution. I just want to know that there is some solution between -1 and 0. So, well, if I could solve it, if I had a formula, I would be happy. Unfortunately, I don't remember any formula for solving cubic equation. So instead, I'll try doing this thing. Let me denote this thing by f of x. It is some function after all. It is continuous. Obviously, it is defined by a very nice function f cubed, x1, sum, so it is continuous. At the point -1, its value is what? -1 minus another one and plus 1 is -1. At the point 0, it is already 0 plus 0 plus 1, 1. So what happens here? This value is negative. At the point -1, the function is negative. At the point 0, it is already positive. Conclusion, by this theorem, there must be a value in between when it's exactly 0. To go from a negative value to a positive one, you must cross a value where it's 0. So hence, by intermediate value theorem, by this statement, there is x between -1 and 1 and 0 such that f at the point x is equal to 0, i.e. the solution of this equation. So even though this statement is very, very simple and very intuitive, it is powerful. It gives you a way to, well, not solve complicated equations, but kind of get some information about the solution. Not the most precise, but some information. Yes? T? Oh, it's intermediate value theorem. So it's this statement. Yeah?
I think what he meant was like there is mapping and then ST.
Oh, such that. Sorry. Yes. Sorry. Why is x in between? So I'm saying at the point -1, my function is negative. At the point 0, it is positive. So I'm in this situation, but now the graph looks like this. At the point -1, my function is negative. At the point 0, it is already positive. Conclusion, whatever the graph is, it must cross this line somewhere in between these two points. Okay, so please do remember to come on Thursday at least for the last 10 minutes.
What's the question?